Good afternoon and welcome. It's a little bit of complex, but I have tried to make it very simple. Neural network in 1 hour. My name is Ravishankar. I'm a consultant in the daytime, in the morning and evening I'm a CTO, and on weekends I'm a trainer. I will try to make it simplified, but please pay attention to the next 1 hour because we are going to blend mathematics and science into a capsule. The best way before I start is that, can you please show off your hands if you are familiar with neural networks and you are doing programming with neural networks? Good. Yeah, few of you are already familiar, so just bear with me if I am going too fundamentals. For the rest of the people, please attend. And we'll start with a simple question. What's the difference between traditional programming and machine learning? In traditional programming, you write the functions, you write your conditions, you write the rules, and you give the input to that particular code that you have written in whatever language you chose, and then you get the output or the decision. In machine learning, the things are a little bit different. In machine learning, you are going to give the data and the outcome as the input to a machine, and you are telling the machine to find out the rules that you have written manually earlier. And you are telling the machine to go on, analyze that historic data and the outcome, and then predict what should be the output. That's the difference between normal programming and machine learning. And let me give you an example. I want to find the maximum of two numbers, A and B. If A is greater than B, that is the code that I'm writing, assuming that I'm not using any standard functions. And if A is greater than B, return A, otherwise return B. With the experience and the knowledge of the programming paradigms, we wrote that particular rule, but as far as machine learning is concerned, you are going to give A and B and the output to that particular code, and you are telling the machine to analyze such cases, samples, and telling the program to create what can be the function which will give you the correct result. So, the difference is that in machine learning, the input and the output are going to the program or the computer, and you are telling the computer to give me the function. Very interesting. There is nobody who has invented that if I give an input and output, automatically give me the function. Think about that. I can create an automated mapping tool, an ETL tool. No ab initio, no data stage, no Informatica, no Pentago, no Kettle, nothing. Nobody has written it in a 100% effective way. But in machine learning, by training all this data, you are trying to create that. But we don't call it as a program. The program is not a correct word. What's the best word? Instead of a program, we call it as a model. And now, if you are looking through machine learning, in all the cases, if A greater than B is very simple. But how about I want to recognize a digit from an image? Machine learning is a science which will help you to train this particular data, first produce some wrong result, say 7, repeatedly iterate through that particular process, find out some of the parameters that are measuring or deciding the values, and finally create the output. And that's what is happening in machine learning. Now, a little bit of terms which will be useful to you as I go along. What's an epoch? If you are iterating through your data many times by shuffling the data repeatedly, those are called epochs. And some simple machine learning algorithms, you may use one epoch, but as your machine learning problem is becoming more and more complex, more and more epochs might be needed. Now, what's the difference between a population and a sample? Assume that I want to analyze the data of the people who are having diabetes. I cannot get that entire data of the entire world of the people who are affected by diabetes. That's called population, the bigger circle. What we do is we take a sample, and that red circle is called a sample. And on that sample, if you are doing the analysis, the main difference between a sample and a population is that the population has got parameters, whereas sample has got statistics. What are those symbols? N is the number of samples, sigma is the mean, and mu is the mean, and sigma is the standard deviation. One sample may not be enough. That's where you will create many samples. Now you may ask a question, if I want to analyze the entire world of the people who are affected by diabetes, and if I am taking some samples and I am analyzing it, how can I predict it in a general way for all that people who are affected by diabetes? This is where a beautiful principle is coming in. So, if you look at this particular graph, which I will give you the link, and if I am looking at this graph, it allows you, it's an applet, and you know in an applet you can just take the mouse and you can create whatever way you want. This is the distribution of the people affected by diabetes, let us say. Some places it's very high, some places it is very low, some places it is high, down, vary. You create whatever sample that you like. And then let's do something. Let's create some samples from it by taking one by one. Click on this animated button. 5 samples. 1, 2, 3, 4, 5. And you look at the mean. The third one is plotting the mean. And again, I am going to take the samples. Again, it is going to plot the mean of the next 5 samples. Again, I am going to plot it. And go on and plotting it. What you see? A beautiful, amazing mathematics there. Whatever be the varying population across the world, finally when you take n samples and if you draw that distribution, you get a normal distribution. So, taking samples and analyzing and applying machine learning is a beautiful strategy. Why? Because as this indicates, whatever be the type of population that you have, and when you take samples of that population and you create analytics or machine learning on the top of it, that's going to give you the correct result. Coming back to our presentation, what is this theorem called? Central limit theorem, one of the very important theorems in statistics. Yes, now next important concept is that whenever you are having a lot of input data, what parameters of that data you are going to take. For example, if you want to analyze the people affected with the diabetes, and if you want to find out a medicine, an effective medicine, what parameters you should take? Of course, there are prominent parameters like the blood level, etc., but what other parameters that you are taking? So there is a beautiful science that is coming in which is called DFS. You can search it whenever you get time. Deep feature synthesis is a new technology which is allowing you to go through all your input samples, apply some functions, and it is going to show you the features that are not known to you otherwise. So feature extraction is another important facility that you will be using. Anyway, this is not our topic. This I just explained to you in order to give the context. Why? Because later I will be using all these terms while we are doing some coding. And we are going to code a hang glider as well as an A380. right in front of you. Well, for that, let us start by asking, hey, there are so many libraries that are available. Why can't I use those libraries? TensorFlow is there, Keras is there, Microsoft Cognitive Toolkit is there. Yes, these are all fantastic libraries, but if you are started using it, you will not know the underlying fundamentals. And the session today is meant to give you the internal architecture, the internal working of how a neural network is, which will help you to use these libraries when you become a professional. So this is not the best place to start with. This is the best place to end with. So, the very fundamental core of artificial intelligence is based upon how humans think, inspired by the concept called a neuron. What you see on the top is the biological neuron, and what you see below is the mathematical neuron. Well, to go into this definition, whenever you hear about neuron, think about this picture. A neuron has got inputs, it has got some weights, it has got something called a bias, and all these will go through an activation function, sometimes also called as a transfer function, and then the output is getting created. Well, that is a neuron. How will you mathematically represent a neuron? The best way to do is to call it by another name called a comparator. Called a perceptron. A perceptron is different from the generalized neuron. How? The activation function that you have seen in the previous deck, that activation function is a comparator, which means that it is asking whether the input is greater than 0 or not. If the input is greater than 0, output is 1, otherwise it is 0. Only two possible cases, 0 and 1. Well, let's give an example. Assume that there are 3 inputs with weights 0.5, minus 1.0 and 1.5, and assume that the bias is minus 1.5. And let's give 3 inputs to this, 8, 5 and 2. What's the output? Do that calculation. 8 into 0.5. So you are multiplying this input by this weight plus this input plus this weight, this input multiplied by this weight plus the bias. You got a 0.5. 0.5 is greater than 0. So the output is 1. That's all. There is a small problem there. Before that, let me define 2 terms. A perceptron or a neuron has got 2 states. One is called a long-term state. The long-term state defines the behavior of the neuron. All the weights and the bias together is called the long-term state of the neuron. And it has got a transient state in which there is an input and there is an output. Okay? Now, let's assume that we want to create a Nand gate, assuming we are having off 0 and on as 1. You know, Nand stands for not and. Obviously, the truth table is given below. Only when 1 and 1 are given as the input, the Nand gives you 0. Otherwise, it is going to give you 1. How will you implement a Nand gate using a perceptron? If I give this weight, W1 as minus 2, W2 as minus 2, and the bias equal to 3, 100%, whatever be the input you are giving, 0 or 1 or 1 or 1, you are going to get the correct result, guaranteed. Because I know, I made up these values. What if I didn't give you that particular values? And I'm telling you to write a program, or I am telling you to use a machine to find out what are those values. How are you going to do that? Let's do that. We will start with 2 random numbers for the weights as well as another random number for the bias. I don't know what it is going to be. Actually, these are big random numbers, but for the sake of the example, let's take these are the 2 small random numbers. So, 2 random numbers and a weight. And now, I'm going to train this particular data by giving a 0 and 1. So, the input is 0 and 1. And you know very well that 0 NAND 1 is 1. Keep that aside. Let's find out what this is going to give me, or what is the result. If you do the multiplication of 0 multiplied by 0.2 plus 1 multiplied by minus 0.3 plus the bias, you are going to get minus 0.4. And as you know, minus 0.4 is less than 0. So this output is 0. The desired output is 1 because 0 NAND 1 is 1. But we got a wrong answer. That's okay. What changes I should make into this weights and the bias in such a way that a small change can make a significant effect in that particular output, so that slowly it starts moving towards the desired output. Here there is a big problem. Assume that I change it to 0.3. Is there any change that is going to happen? No. Assume that I'm going to change it to, let us say, minus 0.4. There is a big problem here. What's the problem? We are using an activator function which is giving you only 2 possibilities of the output, 0 or 1. As long as the output is going to be 0 or 1, our model is not conducive to learning. It cannot. You need to make a significant change in the input weights and the biases in order to make a significant change in your output, as long as it is 0 and 1. Well, let's smoothen it. Now I'm happy. Why? It is not only 0 and 1, it is now accommodating the fractional numbers as well. And what is this called? Logistic sigmoid, the next important term in machine learning. A logistic sigmoid is going to give you a value which can accommodate fractions, and that is very useful. Why? Because in multi-neural networks, one neural network or one layer of the network is going to give the data to the other network, and from there it is going to the other network, the feed-forward strategy. There, in order to make that application rich and expressive, I need to have fractional numbers. But there is a big problem. What is the formula for this logistic sigmoid? If you have learned about order of n notation for the computational complexity, this is very complex to calculate. And you know that in machine learning you are training millions and trillions of data, and if you are using this particular function, you will have to rely on many GPUs, many TPUs. People have experimented on this and found out something better, which looks like this. Very nice. And since there are straight lines, you know very well that there is no exponential equation is coming in. And what is this called? It is very easy to calculate than to pronounce. It is called a ReLU, rectified linear unit. A ReLU is a very simple function, a very simple realization of the logistic sigmoid, where it is giving you if x is greater than 0, x, otherwise it is 0. Still there is a problem. What is the problem? You have handled the right hand side, but again, for all the outputs where the output is going to be 0, still we are having a problem. So let's do something. I'm going to pull it down a little bit, and I'm going to call it as a leaky ReLU. A leaky ReLU is a little bit different from the ReLU in only way that instead of 0, it is going to give you x by 100. Fine. Whenever in any neural network programs you see leaky ReLU as the activator function, remember, this is the reason. So you got leaky ReLU. And now, let us come back. You know very well that the leaky ReLU is going to give you fractional numbers now. But what is our final output that we need? Either a 0 or a 1, correct? Because NAND gate gives you either a 0 or 1. So how are you going to convert this particular fractional output into a 0 or 1? Assume that you got a 0.2. Let us create a strategy. The strategy is that if I am getting an output which is less than 0.5, I will consider it as off, 0. And if I am going to get an output which is greater than 0.5, I will consider it as 1. Now you've got a beautiful architecture which you can measure. You can measure the correctness. And that is very important in machine learning. Why? Because if you are not able to measure the correctness, then you will not be able to iterate and you will not be able to improve. Improving at each iteration is the secret of machine learning. So what we are going to do is that we are now going to calculate and we are going to get a 0.2, and in order to make the things simplified, let us introduce a new term called error. If the desired output is 0 and the actual output is 0.2, you subtract desired output from the actual output minus desired output. That's called error. If the desired output is 1, what is the error? Minus 0.8. Actual output minus desired output. If the desired output is 1, you are going to get 0.2 minus 1, which is 0.8. Very interesting. Now you got the calculation and everything that is needed for creating your network, right? Now you can go through all the samples and find out all the errors. But there is a big problem. Assume that I got 4 samples, and when I executed that 4 samples, 0.2, 0.2, 0.2, 0.2, you know 0.2 is correct. Whenever you get less than 0.5, as the previous deck shows, you are going to get a correct value. So you got the total error. How much is the total error? 0.8. Now let us think about another scenario. This is a very important concept. Let's assume that first 3 I got absolutely correct, but the 4th sample I got 0.6. What is 0.6? Big mistake. But what is the total error? Oh, that is very bad, right? When everything is correct, you got 0.8. And when something is very mistaken, you got a lesser value. You are going to overweight those errors if you use that algorithm in your neural network. It will not work. How can you rectify this particular problem? Take the square of the error. And the moment you take the square of the error, now you are going to punish the bigger errors more than the older approach, mathematics. And now a little bit of nuisances. Sorry. So, we are going to punish the errors more. So, we are going to calculate the total error in this particular format by taking the square. And now, you are trying to reduce not the error in this case, but something else. What is that called? It is called a loss. So never say in machine learning you are going to take the output and you are going to reduce the error. You are reducing the loss. And loss is not an error. Loss is nothing but the sum of the error square. And what is error? Error is actual output minus desired output. Beautiful. Once you have this particular approach, little bit of adjustments you can make. Just now we have told that loss equal to sum of the error squared. If you are trying to reduce the loss, sum of the error squared, it is equivalent to reduce half of sum of the error square. Why? It is going to create a beautiful, nice mathematical symmetry which you are going to see soon. And those machine learning guys already know it. And instead of sum, you can use average. And sometimes loss is also called as cost. Cost, loss, same thing. Now, it is a very weird statement that I am going to make. In any neural network program, if you are going to search for finding out the code which is reducing half of sum of the error squared, you will never ever find it. Why? Why can't we calculate the loss? Okay, I'm a good driver. And when I'm driving, I try to minimize the accident. But tell me, what is the chance that I will have an accident? One in what?
38.
You cannot find the loss or you cannot reduce loss without actually calculating it. So we won't be able to predict and we won't be able to calculate it. Then what are we going to do? Just to hold on. Let's come back to our example and let's plug in some values as usual. Let's give 0.2 minus 0.5 and 0.1. And now you have the activator function, leaky value. And when you multiply, you are going to get a value, 0.3. 0.3 is on the positive side of the ReLU, leaky ReLU. So you are going to get the output as 0.3. Because the leaky ReLU is outputting, if x is greater than 0, it is x, so 0.3. What's the error now? Actual output minus desired output. Actual output is 0.3 and the desired output is 1. 0 and 1 is 1. So the error is minus 0.7. So now you got a calculation where you are going to find out all these calculations for all the samples and find out the total error, and then you are going to make some adjustment in order to make it correct. Is that correct? No. Why? Remember, just now I told you that if you are analyzing or reducing the error, you are not going to punish the bigger errors. You should never ever be finding or making tuning to your algorithm based upon the error. Then, what we can do? We can do something else. If the actual output is 0.3 and the error is 0.7, I am going to say that I am going to give 7 votes or 7 points, 0.7 points to this particular sample. I flipped the sign, please observe. I am changing the word error to something else. I am saying that I am not reducing the error, but I am saying that if the error is 0.7, 0.7 votes. If the error is 0.1, 0.1 votes. If the error is 0.3, 0.3 votes. So the bigger errors are punished bigger, smaller errors are punished smaller. And that's my aim. Now you got a beautiful algorithm. You find out all the votes for all the samples and then find out the total vote. And based upon the total vote, make an adjustment to your weight and the bias and gradually go on until you get the final answer. That will work, and that's called batched learning. We can make a little bit better way of doing the same thing rather than going for batch learning. How? As we go along, each sample learn rather than doing the collection at the end for all the batches. One by one. As we take the first value, we learn, and then we make the adjustment to second value. What is that called? Stochastic learning. In machine learning, you will do either stochastic or batched. So what we are going to do is, we are going to introduce a new value called learning rate, and we are going to multiply the input words by the learning rate, and that value 0.007 we are going to add it to the weight and to the bias. Why did not I add that particular value 0.007 to weight 2? Please look at the input. It is 0, and there is no effect in making a change to that particular W2. So what do you understand? Before you are making the adjustment to these values, you multiply that weight by the input so that you know whether to make the change or not. And this will handle negative values also. Assume that there is an input called -1. If -1 is coming in, you need to decrease the weight to increase the output. That also will be handled by that. So don't forget to multiply by the input values. That will work. And based upon that adjustment, you are now going to improve at each iteration until you are going through it. And remember, I told you that in the neural network code, you will never find the code for half of sum of error squared. But can you guess, by doing this, I am actually executing that, half of sum of error squared. How? And that is where again mathematics is coming in. So let us plot the input versus error. You know, 1.0 is your actual output, and you are going to have, let's say, 0.3, and you know 0.3 means the error is 0.7, right? Actual output is 1, and you got 0.3, so 0.3 minus 1, 0.7 is the error. Now remember that half of sum of error squared, that imaginary, illusionary thing that I told you that we never calculate, right? Let us plot that graph, even though we didn't calculate it, how it will look like. That's how it will look like. And now interestingly, draw a line from that 0.3 to touch that, and what you got? Exactly. What you got is what you were calculating. And you know that half of sum of error squared, consider it as y equal to half of x squared. What is the differential of y equal to half of x squared? You get y equal to x, which is the slope. Imagine you are sitting on the slide. You are going to move down at a steepness proportional to the slope. In batch learning, you will go down, and in the next sample you may go down like this. In the next sample you may go like this. In stochastic learning, as you go at each and every point, you will be adjusting that particular slope until you reach the final correct value, and this is called stochastic gradient descent. Batched gradient descent is completely different from stochastic gradient descent. Now, if the point is in another place, let's say this place, assume that 0.35 is the value. You are going to get a different slope, and you are going to move only little, half of what you moved earlier. So, even though we never calculated half of sum of error squared, by finding out the input words and by doing some mathematics and adjustment onto that, in effect, we are doing that. So what's the algorithm? Stochastic gradient descent for every training sample, find out the slope, and then every time step that particular slope by subtracting the slope by the learning rate. So what you are waiting for? We are going to build it now. And I'm going to build first the Nand gate. So open your favorite editor and take the code. First we will look at Neuron.java. I have mentioned one slide earlier telling that you have to separate the long-term state and the transient state. That is a good programming practice. So I am going to create a neuron. Don't worry about the object-oriented programming strategies, methods and all here, that my variables should be private, public, a get and a set and all. No, I don't follow all those things. We are representing a neuron, and in that neuron, we have got a weight 1, weight 2 and bias. We initialize the values by calling small random numbers. That's all, which is my neuron. And once the neuron is completed, then I am going to create a transient state, and I'm going to call it as firing neuron. And in firing neuron, you know that the total input is the state. It references the neuron, and there is an output. And then you are going to call the fire method. And what is fire method? Input into the weight 1 plus input into weight 2 plus the bias. And you are going to apply the ReLU. And you know what is the ReLU. If the total input is greater than 0, it is total input. Otherwise, it is total input divided by 100. Everything very clear now. Now you have a learn method. And inside the learn method, you fire the input 1 and input 2. Then you calculate the output votes. Remember, whenever you are doing the output votes, you are flipping the sign. You got error minus 0.7, but your vote is plus 0.7. So instead of actual output minus desired output, I am going to take expected output minus output, which is flipping the sign. And then you are going to multiply it by the slope of the ReLU. What is this rule called? It is called chain rule in calculus. Whenever you are on the positive side of the ReLU, you will multiply it by 1, because y equal to x is the graph of the positive side of the ReLU. Negative side of the ReLU, the leaky part of the ReLU, it is 0.001. 0.01, sorry. So you will multiply by 0.01, that is the chain rule. And once you are there, just plumb it inside a main.java where you create 1000 samples and you calculate the output for a NAND gate, not AND. And fire the neuron, and then finally print the results. So let's run this. That's the final state that the machine learning has calculated from 1000 samples of zeros and ones. You got the weight 1, you got the weight 2, and you got the bias. And out of 1000 samples, 800 I took as training, and 800 I took as training and 200 for testing, and we got all the 200 correct. Don't be so happy. Why it is correct? Why? Because I experimented a lot of times and I put the parameters accordingly. And somebody who is writing the first time the program, going there and telling that, oh, learning rate, this is a Stanford machine learning algorithm. So I'm going to make the learning rate as 0.9. And then I'm going to save this particular code and come back to here and then again compile the code and then again try to execute and see what you are going to get. Learning rate is very, very important. You have to tune your algorithm in such a way that it is doing the learning rate accurately. Can you tell me what happened if the learning rate is very high in the graphical way? You are in the slide and you are oscillating. And you are never getting an output at all. And that is what is happening here. You are not getting the output correctly. Now, let's do something more. If suppose, where did I change that? In the main.java. Yeah, the learning rate, it was 0.01, I think. Right, and now let's do something more. What I'm going to do is, let's see whether this works for a NOR gate. I'm going to change the symbol. Perfectly all right. It will work for a NOR gate. And you know what you got? Take this particular code, you got the NAND gate, you get the NOR gate, you can create any gates now. You can create any logical network now. It is functionally complete. Again, it is functionally complete, everything is okay, and please don't do this, where I am going to execute an exclusive OR. And if you are trying to compile this particular program again, and if you are executing it, exclusive OR will not work. There is nothing wrong with our code, nothing wrong with our training data, nothing wrong with our learning rate. You can't do exclusive OR with one neuron. You need multiple neurons. And that takes us to our next concept, because what we built is a hang glider, and now let's go and build a A380. Multi-layer neurons, where you are not now dealing with one neuron, instead you are going to deal with multiple layers of neurons. As an example, on the left hand side you have got the input layer, and on the right hand side you have got the output layer. In between you have got so many other layers which are all called as input layers or hidden layers, and all of them are neurons. And you have learned almost everything that is needed to build a multi-layer framework, except how are you going to fire this particular data? First, you take the input. All these are the inputs. Then you are going to give it to these neurons, and you are going to fire each neuron individually, and you are going to get the outputs, and you are going to look at the output votes using the ReLU function, because we want to punish the bigger errors, and wherever most accurate value is coming in, you will consider that as the result. For example, if I am firing this and I got that final output in the output layer, maximum weight is coming in 0.86, so it is an 8. Possibly one very important thing that you need is, when you are firing from this side to that side, that is called feed forward method, which I told you already. When you are doing the training, assume that you fired and you got this particular output votes. How are you going to find out the output vote of the internal neurons, the internal layers? The output vote of this particular neuron is equal to sum of the input votes of all the layer that is processed weighted. That is the only thing that you need extra. Sum of all the input votes weighted, you add it, that will become the output vote for this particular neuron. So hook it up. You are going to get a multi-neural network. So let's do that. And for obvious reasons which you will know now, I used C# for doing this. And what I'm going to do is, I am going to run this particular code. And what I did is, let me check whether I have commented it out or not. Yeah, I'm going to run this particular one. And I have used 50,000 images from the MNIST database, which has got all that images that are needed for character recognition. And it is doing all epochs that I told you. Why? Because here the complexity is very high. One epoch is not enough. So there are many epochs. And I got 96.3 out of the 50,000 images success. And my testing data has got only 95.3 success. Now, why did I use this C#? If you are familiar with the C# programming, you can easily integrate a WPF visualizer Windows presentation framework visualizer, and you can see actually what is happening. So what I'm going to do, I'm going to change a little bit in my code. I'm going to dump this particular result, and I'm going to run it by the visualizer, WPF visualizer. There you go. And the lines that you see here are the weights, and the color that you see on the numbers are the biases. And I'm going to show you that if you look and keep the mouse here, you are going to see that the weights are getting changed, and similarly the biases there, and you got the score. And impressively, I have given a touchpad on the right hand side to give a real-time image recognition. And what I'm going to do is I'm going to write a 1. No, it's 0. It's a 7. Oh, it's a 7. Why? 95.6. Why is it giving a wrong result? I intentionally made it wrong. Why? In the touchpad, you see, I wrote it at the corner. And what about your training images? All are centered. This is one of the very important factors about machine learning. Data augmentation. What is meant by data augmentation? How you trained, in that way you have to give the input. Otherwise, you have to write the algorithm, a processor, to your machine learning algorithm, which is going to take all that images, little bit shifted to the right hand side, little bit shifted to the left hand side, and then do the training, and after that you write it, you will get it. Or, programmers, we do nasty tricks. So, Control F, search for the word gray, and I am going to do sender my image, whatever I am going to type. A very simple way of fixing it, right? So I'm going to write gray data is equal to the sender image of whatever I am going to write. And then I'm going to run it again. Let it go through a couple of epochs. We don't need to wait it. And you understand why I separated the transient state from the long-term state? Because I separated it, the transient state I can take, the transient state I can take and I can parallelize it into a Spark or Flink cluster. So always try to separate it. And now you write one. Beautiful, right? So that was the trick. So whenever you are looking at the data and whenever you are doing the machine learning algorithms, at the time, make sure that your data is properly being trained and is given as the input to this one. Now, just to make sure that you understand the beauty of this particular architecture, this is a very, very generalized framework. So I'm going to go there and I'm going to make it really, really multi-neural. So I'm going to tell here that, okay, 30 neurons first layer, and then another 30 neurons in the second layer, and now I am going to run this particular code, and you can see now that it is a little bit complex algorithm where 2 layers are now into the picture, first layer versus the second layer, and now you can see clearly how this particular application is running. Do you think that adding multiple layers will improve the accuracy and efficiency of your machine learning? In character recognition kind of applications, it is not going to give any effect at all. But there are some other applications, speech recognition, etc., where multi-neural networks and adding neurons will be, adding neural layers will be very, 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 very useful. In this case, it is not that useful. Rather, what I would do is, rather than making it 30, I will give 60 as the one layer of particular neuron. That is the best way. Now, I have briefly mentioned about what will happen if the learning rate is very high. I am going to change this particular learning rate to 0.09, for example. Okay, it was 0.01, and then let us run. Okay, I am going to change it back to our old values, which is 20, and then let's run. And you see what is happening. I will show you the beauty of oscillation. And this is a see how the color is changing, and that's what I told you in the slide. You are keeping on oscillating until you are getting a particular correct result. And now to make it finally a beautiful and efficient program, what I'm going to do is that, please look at the score that you got. It is very less. So I'm going to make it as 100 neurons, And I have written this particular code by subclassing the activator function, which means that I can plug in whatever activator I want, either a logistic sigmoid or a hyperbolic tangent, or I can use a simple ReLU, etc. Currently, it is hard-coded for a leaky ReLU. What I am going to do is net.activators of 1. The first layer activator, I am going to write a new softmax activator with cross entropy. Don't worry about this particular name. It is mathematically very complex, but it is very simple algorithm. Softmax activator with I think there is a spelling mistake. Let me just check the class name that I have given. Control C. Oh, with cross entropy loss, that's that word I was missing. So if I'm changing that into this particular one, and then I am going to keep it, and then I am going to run it. And while I'm running, I am going to go back to this particular slides which we started off, and just let's go to the final set of slides. Oh. All right. Normally you will think that you are going to get this particular gradient descent always. No, you are not going to get. That is a trick. If you get it, very good. But you are not going to get this always. Instead, what you are going to get is this type of gradient descent graph. Normally in machine learning you will see this type of graphs. What is the problem? Sometimes you will end up here, so that there is no further go down, but you will stuck with this particular result. And that may affect your machine learning output. This is called local minima. You may want to avoid it. And the way to avoid is by using the correct activator function and correct learning rate. And remember, we are using small random numbers to initialize the weight and the bias. Sometimes you may come across those particular values at this particular point so that it cannot go. So you may need to repeat your experiment so that you are getting the right result. Ideal case is this. And finally, what is the future? Assume that there is one network created by code on the beach or code on the land. And there is another neural network. Can that neural network learn from this neural network? I think Apple is doing something. It is called generative adversarial neural networks, where one network is going to learn from the other networks. Maybe that's the future. And finally, let's go back to our code where what is the accuracy? You got 94.7, 96.1 as the training score, and 94.7. So you play with it. And you can change the values. Sometimes, if you are looking at a furry animal and you want to decide whether it is a dog or a cat, this algorithm is not sufficient. This algorithm is a general purpose neural network. If you want to customize it for images, you may take the image and you may apply some numbers on the top of that image, and then you will do a matrix dot product on that image to identify the features that I discussed in the beginning. And you will convolute and will apply the features, which is called a convolutional neural network. Data augmentation, convolutional neural network, feature extraction, all these are the additional things that you should be adding to make your neural network perfect and able to be predicted. And finally, if you want to have the code and if you want to experiment on this, it's available in this particular COTB 2019 at GitHub. And if you want to talk to me, want to appreciate me, or want to scold me, ravishankar.nair@gmail.com. Thank you very much.